Right now, we will start up with the next topic is electromagnetism. So, the production of EMF with magnetism. Okay, now magnetism, if we talk about magnetism, it is always related with flux, right? So, by changing the flux or by changing the current flow, the EMF can be induced. Okay. Now, first we will start up with the initial one. What is electromagnetism? Electromagnetism. 1 minute, ma. Right. Now, electromagnetism was initially generated by two main methods. One, by the chemical reaction of the batteries. Okay, first one was the chemical reaction of the batteries, and then by heating the thermocouple at the junction of the uh, junction place where two dissimilar metals are joined. Okay. Now, first, this two were predominantly. If it is going to be from chemical reaction from battery, see, the picture will be like this. From the battery ends, the EMF is generated. Okay. And the galvanometer is connected to measure it. Clear? The second one, it can be done by heating a thermocouple. Okay. Thermocouple, when we join two junctions, two dissimilar metals, okay, at that junction, it is going to get heated. And because of this heating, the EMF is generated. Okay. Now, the third method was discovered by Faraday. Okay. Now, here, when there is going to be the change in flux, now you can see here the magnets are there. From this is the north pole and this is the south pole. Okay, and the flux lines flow from north pole to south pole. And if this flux lines are cut by any machine or any other device, okay, so EMF will be generated. So this is the production of EMF. Okay, so we will be dealing with this electromagnetism and different types of electromagnetism we will be dealing. Okay, and we will be having small problems. Okay, all these problems will be direct substitution problems. Clear? Now, I told you what is electromagnetism. The EMF may be produced either by batteries through chemical reaction or by thermocouples, by heating the junction of two dissimilar metals. Okay. After that, later only, Michael Faraday discovered that the EMF can also be produced by electromagnetic induction. Now, this electromagnetic induction, the production of power with this electromagnetic induction is used commercially in generation of power. Okay. Now, after the generation of power, it is getting transmitted, it is getting distributed, right? So the initial one is the generation. Now, this electromagnetic, what is this electromagnetic induction? We have to know. Whenever the magnetic flux linking with the coil changes. So magnetic flux linking with the coil changes means, see, the flux is here. Okay, the flux flows from north pole to south pole. So when the flux linking changes means when, see, I'm going to place a, okay, when this coil is going to rotate, assume a coil is placed, a coil or a conductor, anything. Okay, now this coil or conductor is going to be rotated. Assume it is going to get rotated. When it is going to get rotated, what happens? The flux line linking with the coil changes. Okay, now as this flux line linking with this coil changes, EMF will be induced. Okay, EMF will not be induced if it is stationary. Okay, if there is no flux lines cut, okay, there will be no EMF induced. EMF will be induced only when the flux lines are cut. Okay, and it changes according to the variation of the flux also. Clear? That's what is mentioned. Flux linking with the coil changes and EMF is induced in the coil. This phenomenon is called as electromagnetic induction. Okay, now applications, microphones, telephones, transformer, generator, motor, all this thing ma'am has explained, I think. See, you know what is a motor? Motor converts electrical form of energy to mechanical form. The generator is the vice versa. Generator converts the mechanical form into electrical form. Okay. And transformer is not involved with any energy conversion. Okay. It steps up or steps down the voltage. Okay. Here the principle of mutual inductance will be there. Transformers. So these are some of the places where the electromagnetic induction is applied. Okay. Now, what happens in the electromagnetic induction? Actually, the EMF is produced, right? By varying the flux lines, we are producing the EMF. Now, this induced EMF, okay, induced EMF is broadly classified into two: dynamically induced EMF and statically induced EMF. Okay, dynamically induced EMF, as the name tells, dynamic. Dynamic is involved with the movement. Okay, either the magnet can move or the coil can move. I think you will understand what I'm telling. See, this is the magnet. Okay, this is the magnet, and this is going to be the coil. Okay, so the flux lines will be cut. Either of the two moves. Either if the magnet moves or the coil moves, right? So there should be some change of flux. That's all. Either the coil can move or the magnet can move. Okay. So whenever a movement is involved, then we call it as dynamically induced EMF. Okay. The next type is statically induced EMF. Statically induced EMF, as the name tells, statically means it is going to be stationary. So neither the conductor moves nor the magnet moves. Okay. But here what happens? The current flowing through the coil will change. Okay. The current flowing through the coil can be changed, right? How? Either by varying the supply, right? So when the current moving in the coil changes means then the induced EMF will also change. Okay. So here in the dynamically induced EMF, the example is AC or DC generator, and statically induced EMF, the example is transformer. Okay. Now one more time I will tell you, dynamically means it is involved with movement. Statically means it is not involved with movement, it is stationary. Okay. So dynamically induced EMF, when conductor is moving in a stationary magnetic field or moving the system while keeping the conductor stationary such that the flux linking the conductor changes. Okay. Either if the magnet moves, the conductor is kept as stationary. If the conductor moves, the magnet is kept as stationary. Okay. The term dynamic is used since conductor is in motion. Clear? Next, statically induced EMF. Here, the conductor is stationary and the magnetic field is changing. How is the magnetic field changing? The magnetic field is changing by the movement or flow of the current through it. Okay. The word static means stationary. Clear? Now, next, production of induced EMF. Now, I told you this induced EMF, how all we can produce it. Okay. Now, three things are involved. One is the magnet moving. Okay. The other one is the coil moving. Okay. The third one is going to be the current, the change of current. Okay. Now, first method. See here, let me assume a magnet with north-south poles. The magnetic lines of forces flow from north pole to south pole. Okay. Now, here, if I'm going to bring this magnet near a coil, assume a coil is kept here. Okay. Wounded with and connected with a galvanometer to measure. Okay, this galvanometer will be showing me the deflection. Clear? When the magnet is moved towards the coil, now when this magnet is moving to the coil, what happens? The current will be changing, right? That is indicated by the galvanometer. Okay. Now when this 1 minute, when this magnet is taken nearby the coil, right, there will be more deflection. And when this magnet is taken away from the coil, there will be less deflection, right? So what will happen? Then there is going to be change of flux. Okay, the flux linking with this coil changes. So As a result, EMF will be induced. Okay, when the magnet is moved towards the coil, there is deflection in the galvanometer connected across the coil, thus indicating the flow of current. Okay, this current is due to the induced EMF in the coil. Okay, a change in the flux results in the production of EMF. Presence of EMF gives rise to the flow of current. Clear? The flux, whenever the flux changes, there is going to be EMF induced. This principle is called as electromagnetic induction. Clear? If the magnet movement is stopped, the pointer will show zero deflection. That is the very, very important point. If there is no movement here at this in this arrangement, the EMF induced will be zero. Okay, this is very, very important. This is method one. Okay, if the magnet moves with higher speed, or if the number of turns of the coil is increased, or if we use the stronger magnet, we can observe greater deflection of the pointer. This is how to improve the generation of EMF. Okay, as the magnet taken away from the coil, the flux linked with the coil is decreased. The deflection of the galvanometer is in opposite direction. Okay, whatever I explained you, the same thing. When this is taken in front, when the magnet is going nearby the coil, there will be greater deflection. When it is taken away from the coil, the deflection will be less. Okay, and when this is going to be stationary, there will be no change in the galvanometer. As a result, the EMF induced will be zero. Clear? This is method one. So method one, we are changing the magnet. Okay, method two. Now method two, assume here this is the magnet, what I had told you already. Okay, this is the conductor. So coil or a conductor, anything it can be. Okay, now when I'm going to rotate this conductor, rotate or change the position of conductor, what happens? There is going to be the change of flux lines. Okay, the number of flux lines cut is going to be changed, right? So as a result of this, EMF will be induced. Okay, so this is represented by the galvanometer. Okay, the same way, when more flux lines are cut, there will be more deflection in the galvanometer. When less flux lines are cut, the EMF induced will be less. Okay, and if the conductor is going to be stationary, if it is not going to have any flux lines cut, then what happens? The EMF induced will be zero. Clear? The EMF can also be induced in the coil by moving the coil and keeping the magnet stationary. These two methods of producing the EMF are called the dynamic methods. Okay, so that's what I told you. The EMF, induced EMF, is divided into two major classification. One is going to be dynamically induced, and other one is going to be statically induced. Dynamically movement. So in the dynamically induced EMF, either the magnet can rotate, or the conductor can rotate. Okay, next, method three. Now method three, we are going to have it as the statically induced EMF. Okay, statically induced EMF, what did I tell you? There is going to be no movement. Okay, but there will be change of current flowing in the coil. Okay, this coil we have, right? This coil, the current flowing will be changed. Okay, so how to do that? Now see here, let me assume two coils. Okay, coil 1, coil 2. One second. Coil, this is coil 1, this is coil 2. Okay, now let me give a supply of voltage V1, okay, for the coil 1, and let me take, this is going to, the coil 1 is going to have n1 number of turns, and coil 2 is going to have n2 number of turns. Okay, now as I'm going to give a supply here I'm going to have a switch. Okay, I will close the switch. So when I close the switch only, what happens? The supply, the coil is going to get activated, a current of I1 flows through it, right? Now this current of I1 induces a flux phi1 in the first coil. Okay, so that is, okay, I1, I1 is induced. Now this phi1, what does it do? It links with its neighboring, okay? Which is the neighboring coil here? Coil 2 is the neighboring coil, okay? This flux phi1 induces some flux to the nearby or the neighboring coil, okay? Let me take the flux induced here to the neighboring coil is phi 2. Okay, so this phi 2 is induced due to phi 1. How does this phi 1 is arising? This phi 1 is arising due to the flow of current of I1. Okay, now this flux phi 2, which has got induced in the neighboring coil, induces a current I2, okay, in its own coil. And because of this current I2, a EMF is generated, which is measured in the galvanometer, which is connected to the last end of this second coil. Clear? I will repeat once again. We are having two coils. Let me take it as coil 1 and coil 2. Okay. Now, in the coil 1, we are giving the supply V1. Okay. And the switch is closed such that the supply is given to coil 1. Okay. So, because of the supply, a current of I1 flows through the coil 1. Okay. Now, because of this current I1, a flux phi1 is generated in the first coil. Okay. This flux phi1 gets induced to the secondary coil. Let us take or let us assume the flux induced in the secondary coil is phi 2. Okay. Now, what does this phi 2 do? This flux generated will be generating a current I2 in its own coil. Okay. And this current I2 will generate a EMF, which is called as the statically induced EMF. Okay. So this is the EMF. It can be measured by the galvanometer. Okay. Now, statically induced EMF we are calling because there is no movement in the conductor or the magnet, but there is going to be change in the current. Okay. So this is the method 3. This is called a statically induced EMF. Okay. Now I'll read out once again. Both conductor and magnet are kept stationary and change in flux is obtained by changing the current. This method of EMF prediction is called statically induced EMF. Okay. So this is the methodology which is used in transformers. Okay. In the transformer, we will be having two devices. Okay. Two coils, primary winding and secondary winding. Okay. How to define a transformer is a static device with the help of which you can step up or step down the voltage or the current according to the requirement. Okay. Now next we will move on to Faraday's law of electromagnetic induction. Now I have told you what is electromagnetic induction, right? Electromagnetic induction, EMF is generated according to Faraday's law. We will tell you according to Faraday's law, E is equal to N d phi by dt. Okay, so N d phi by dt, N into rate of change of flux. Okay, this is what is given by Faraday's law. Okay. Now Faraday's second law states that E is equal to N d phi by dt. The same what I have written here, the same thing. Okay, in the first law, a EMF is induced. Faraday's law of electromagnetism, we have two laws. First law, the EMF is generated due to change of flux. Okay, and second law, we have the expression E is equal to N d phi by dt. Okay. Right. Now we will proceed. See here with the definition. See, definition is very, very important, ma. Whenever the conductor, first law, whenever the conductor cut across the magnetic field, an EMF is induced in the conductor. Okay, or whenever the magnetic flux linking with any coil changes, an EMF is induced in the coil. So whatever we have done till now, the same thing we are defining as the Faraday's law. Okay, that's what is given by Faraday's law. Whenever the conductor cut across the magnetic field, an EMF is induced, or whenever the magnetic flux linking with the coil changes, EMF is induced in the coil. Okay. Now, what is second law? Second law, see, we have already seen that when the flux line changes, when the flux line flux linking with the coil changes, EMF is induced. Okay. My doubts we will have in the last 10 minutes. Okay. I'll complete the syllabus as of now. So let us have the magnitude of the induced EMF is equal to the rate of change of flux linkage. Now, what is this flux linkage? Flux linkage is defined as N into phi. Okay, N is the number of turns and phi is the flux linkage, flux produced. Okay, suppose a coil has N turns. Let the flux through it change from phi 1 Weber to phi 2. See, it is going to change from when there is going to change of flux only EMF is induced. Clear? When if it is not changed, then EMF is equal to 0. So when we are going to take change in flux, we are going to add two fluxes, phi 1 and phi 2. Let the initial value of the flux be phi 1 and the final value of the flux be phi 2. Okay, and let us take it is going to be changed in t seconds. Okay, so let the flux through it change from phi 1 Weber to phi 2 Weber in t seconds. Product of n into phi is called flux linkage. That's what I told you. Okay. Flux linkage is given by n into phi, where n is the number of turns in the coil and phi is the flux. Okay. Now the initial flux linkage is n into phi 1 and the final flux linkage is n into phi 2. You already know the number of turns is constant, so number of turns will not change, right? So but the flux link will change, right? So the initial flux linkage is n phi 1 and the final flux linkage is n phi 2. Okay, now we are going to derive the value for E is equal to n d phi by dt. Okay, we are arriving that, that's all. Now change of flux linkage. What is this change of flux linkage? N into phi 2 minus n into phi 1. Okay, because we know the final flux linkage minus the initial flux linkage. Okay, final flux linkage is n into phi 2 and initial flux linkage is n into phi 1. Now as n is common, we will just remove it, n into phi 2 minus phi 1, or rate of change of flux linkage is equal to n into phi 2 minus phi 1 by t. Rate of change of flux with respect to time, right? So n into phi 2 minus phi 1 by t. Okay. So if uh, E is the induced EMF, okay, then according to Faraday's law, we can write E is equal to n d phi by dt, right? Now that's what is this? You're able to understand, I think. See, this is n d phi by dt. Okay, n into rate of change of flux. Rate of change of flux is going to be d phi. So we will call it as d into phi. Okay, divided by, see here rate of change of flux. So rate of change of flux means, so the time is also included. So we will put it as dt. Okay, so that's what has been mentioned here. E is equal to n d phi by dt. Okay, now actually the direction of the induced EMF is so as to oppose the very cause producing it. So what is this? This is the Lenz's law. The Lenz's law gives the direction of the current flow. Okay, so you call it as E is equal to minus n d phi by dt because always the current will be opposite. The current flowing will be opposite. The cause producing it will be in the opposite direction. So you put a negative sign here. So E is equal to minus n d phi by dt. Okay. This is very, very important, this formula. This formula you will be using it everywhere. Okay. 1 minute. Okay. Now, to produce the induced EMF in a conductor, there must be a rotating magnetic field cutting the stationary conductor. All these points are very, very important. We will just go through before moving to the next one. Okay. EMF is also induced. EMF is also induced when a moving conductor is cut by a stationary magnetic flux. Okay. Whatever we had seen it, the same points are getting repeated. When there is no relative motion between the magnetic flux and the conductor, no EMF is induced in it. Okay. The direction of the induced EMF in the coil depends upon the direction of the magnetic field and that of the motion of the coil. So it depends upon the both, okay, conductor and the magnet. If the conductor is moved parallel to the direction of flux, it does not cut the conductor. Hence, no EMF is induced in it. You understand this? See, in this diagram, if this coil, if the conductor is in the horizontal position, it is in vertical position here, right? If it is in horizontal position like this, okay? If it is in horizontal position, what happens? There will be no linking of flux with the coil, right? The flux linking with the coil will be zero. So what happens to that then? The rate of change of flux induced, the rate of change of flux linking with the coil is going to be zero. So as d phi by dt is equal to zero, what happens? E is equal to zero. That's what I'm telling you. When it is going to be horizontal, the flux linking with the coil is zero. So E is zero. That's what is mentioned. Okay. Next. Now we are telling this EMF. Okay. This induced EMF, now we had given the direction of the current flow, right? The direction of the current flow is going to be opposite according to Lenz's law. But we exactly wanted to mention the direction. So we will be stating it by Fleming's right hand rule and Fleming's left hand rule. Okay. Already you would have come across all this Fleming's rules, right? Fleming's, first we will start up with the Fleming's right hand rule. So Fleming's right hand rule. Fleming's right hand rule. I'd given the picture also. Any one of you tell me? So first point will be stretch your forefinger, middle finger and thumb of your right hand such that they are going to be perpendicular to each other. Okay. Next, what is forefinger gives? Forefinger gives the direction of the, I wanted you to give me in the chat box. Forefinger gives the direction of the, it has been mentioned also in the diagram. You can see and tell me. Very good. So the forefinger gives the direction of the magnetic field. What about the middle finger? Middle finger gives the direction of the current flow. Right, direction of the current flow. Then the gives the thumb gives the force of the force exerted by the conductor. Very good. Right. We will just go through this once again. Okay. It has been given here in the diagram. See, the the forefinger represents the field, magnetic field. The middle finger represents the current, and the thumb represents the force of the conductor. Right. Very good. Yes, Arul, we will be defining that also. Right. Stretch out. Once again, we will go through Fleming's right hand rule. Stretch out the forefinger, middle finger, and the thumb of the right hand such that they are mutually perpendicular to one another. If the forefinger points in the direction of the magnetic field and the middle finger points in the direction of the current, then the thumb points in the direction of the motion of the conductor. Okay. Now, the direction of the dynamically induced EMF can be determined by Fleming's right hand rule. Okay. This rule is applied for DC generators. Always you remember, right hand rule, on your right hand, you'll be having a generator, and on your left hand, you'll be having a motor. So Fleming's right hand rule is always applied to generators. What is a generator? Generator is a machine which converts mechanical energy to electrical energy. Okay. And on your left hand, always Fleming's left hand rule. Okay. Fleming's left hand rule is also similar to the right hand rule with a small change, right? Now Fleming's right hand rule. We'll go for the statement. Fleming's right hand rule. Again, the first point will be the same. These laws, the Lenz law, Fleming's right hand rule, Fleming's left hand rule, Faraday's law, many a time they had asked. Okay, always they are asking it. Okay, so be thorough with the definitions. Clear? Coming to Fleming's left hand rule. So Fleming's left hand rule, the forefinger represents the magnetic field, the middle finger represents the current flow. Okay, and then the thumb gives the motion of the conductor. Okay, or the force exerted by the conductor. The first point is the same. First point, the forefinger, middle finger and the thumb is going to be stretched, okay, with with mutually perpendicular to each other. Okay, that is going to be the first point, and then you will be giving the definition. Okay, we'll read out once again the definition, then we will move out. Okay, stretch out the forefinger, middle finger and thumb of the left hand mutually perpendicular to one another. If the forefinger points to the direction of the field and the middle finger points in the direction of the current, then the thumb indicates the direction of the mechanical force exerted by the conductor. Okay. So this rule is applied for DC motors. So always you remember, on your right hand generator, on your left hand motor. This is how you're going to remember. Okay. The next one, Lenz law. Lenz law we have already seen. In effect, electromagnetically induced EMF enhances the flows in a coil in such a direction that the magnetic field set up by it opposes the very cause producing it. So to represent that only, we are putting in the equation minus. Okay, the direction of statically induced EMF, Lenz law is used. So we put the equation as E is equal to minus n d phi by dt, right? So minus n d phi by dt, this negative sign is representing the direction. It is just stating that it is going to be opposite. That's all. Okay. Next. Now, coming to the types of induced EMF. Yeah, it'll oppose, Rashmita. Yes, correct. That's what I mean to tell. Now, types of induced EMF. Now we know what is EMF, what is induced EMF, right? Induced EMF is broadly classified into statically induced EMF and dynamically induced EMF. I have told you, dynamically means it is going to be movement, and statically means it is going to be stationary. Now, the statically induced EMF is again classified into self-induced EMF and mutually induced EMF. Okay, the self-induced EMF is the EMF induced in the own coil. When the current changes in the coil, there will be change in the EMF induced, right? That is called as self-induced EMF. Okay. The next, mutually induced EMF. If the current in the neighboring coil changes, okay, there will be a change of flux linkage in the second coil, right? So because of that, the EMF changes. That is called as mutually induced EMF. Clear, ma? So this is the difference. Self-induced, the change in the own coil, and the flux linkage change in the own coil, and mutually induced EMF, the flux linkage is related with the neighboring coil. Okay, right. Now we will explain about this again. When the flux linking with the coil or conductor changes and EMF is induced in the coil, so we call it as all this we have read. Okay, dynamically induced EMF and statically induced. Now, in dynamically induced, first starting up with the dynamically induced EMF, when the conductor is moved in a stationary magnetic field, or when the magnetic field is moved by keeping the conductor, and EMF is induced, provided the movement is done in such a way that the conductor is moved across the magnetic field. Okay, the EMF thus induced is called as dynamically induced, right? So this is the one we are going to be used in AC or DC generators. Okay, now let us consider this diagram. Okay, so we have the magnet, north and south pole, and there is going to be the flux lines flowing from north to south pole. Let us assume a conductor is placed in the magnetic field like this. Okay. Now let us assume the conductor is going to be placed in a uniform magnetic field of B. Flux density B. Okay. So you know what is the unit for flux density, ma? What is flux density? How to define flux density? How to define flux density? Flux density is represented by B. Okay. What is the formula for flux density? Vamsi, good. Phi by A. Yeah. Yeah, phi by A. Okay. Now we are going to use that formula. We know B is equal to phi by. Okay. Now let me assume this conductor. Okay. This conductor is of length L. Okay. Small L. Okay, and it is going to change from this position to a small position, okay, to the next point. Okay, so let me take the change of position as d into x. Change of distance as d into x. Okay, now what is the area swept by this conductor? Then area swept by the conductor, A is equal to L into dx. Okay, I will put a small l, L into dx. Dx is going to be the change of distance. Okay, we know b is equal to 5, b is equal to 5 by a, and we know a is equal to L into dx. Okay, now we are going to calculate the change of flux value here. Okay, now what is the change of flux value? Change of flux, we will take it as d into phi, because EMF is going to be induced only when there is going to be flux change. Okay, so d into phi is equal to b into a. Okay, or this is written from phi is equal to ba. As there is going to be change, I will mention it as d phi. Now what is this a? Or you can take d phi, this also da you can put. Okay, so da is nothing but the change in the area. Okay, so you can write this as d phi is equal to b into L into dx. B into L into dx. Ah, right. Okay. Now, what is the EMF according to Faraday's law? E is proportional to d phi by dt. Okay. E is proportional to d phi by dt. Now, what is d phi? D phi is equal to BL dx. BL dx by dt. Okay. Now, what is B here? B is going to be the magnetic flux density. Okay, and what is L? L is going to be the length of the conductor. What is dx by dt? Dx is nothing but the change in distance. So dt is the change in time. So dx by dt will be the velocity. So we will write it as b l v. Okay, E is equal to BLV. Okay, this is very, very important formula. Now, if this conductor is not moving in a straight path, if it is going to move in an inclined path, okay, like this, okay, if it is going to move in an inclined path, then the EMF will be calculated as E is equal to BLV sine theta. Okay, giving uh, we will be giving some orientation. We will measure the sine theta cos theta, and we are defining that E is equal to BLV sine theta. Okay, theta is going to be the angle made by the conductor with the uniform magnetic field. Okay, so this is E is equal to BLV sine theta. Okay. So whatever I've told you, we will just go through again. The area swept by the conductor is equal to meter square. Okay, the area swept by the conductor, we are going to measure the area swept by the conductor. So this is going to be L into dx. We have not written there. It is going to be L into dx. The unit is given in meter square. Next, magnetic flux cut by the conductor. The magnetic flux cut by the conductor is equal to flux density into area swept. Okay, flux density into area swept, that is what is given by the formula. B is equal to 5 by 8. So the same thing is written like that. Okay, so this is equal to B into L into dx. Whatever we had seen it, the same thing. By Faraday's law of electromagnetic induction, the EMF induced in the conductor is E is equal to N d phi by dt. If the number of turns is assumed to be 1, then we call it as E is equal to d phi by dt. Okay. Or we know d phi is equal to BL dx. Clear? Dx is going to be the change of distance. Okay. Or E is equal to BL dx by dt, or E is equal to BLV. Okay, this is the linear velocity if it is going to move in a linear manner, or if it is going to have the movement in an inclined way, then we will be measuring the angle theta. The theta is angle made by the conductor with the uniform magnetic field. Okay, and we will have it as E is equal to BLV sine theta. Clear? If the conductor moves at an angle theta to the magnetic field, then the velocity at which the conductor moves is V sine theta. So we will have it as E is equal to BLV sine theta. Okay, right. It is volts. It is volts. The direction of induced EMF is determined by Fleming's right angle. Okay. Now this is as related with the dynamically induced EMF. The next one is statically induced EMF. Statically, you already know if there is movement in the current, or if there is movement in the flux linkage, change in the flux linkage, you have the statically induced EMF. I have told you the statically induced EMF is divided into two: the self-induced EMF and the mutually induced EMF. Okay, the flux linked with the coil without moving either the coil or the field system, but by changing the current in the field system. Okay. The EMF induced in this way without motion of either conductor or flux is called statically induced. This is used in the transformer. Best example is transformer. Okay. Next. Now coming to the self-induced EMF. In the self-induced EMF, the EMF induced in a coil due to the change in the value of its own flux linking is called self-induced EMF. See here. Now consider this diagram. We have the coil here. Okay. We have the coil here. The coil is connected with the EMF. Okay. And the EMF is connected, the other side of the EMF is connected to the resistance. Okay. Resistance, we are going to vary it with the potentiometer. Okay. This is done to change the current. Okay. It is connected with the resistance. When you change the resistance, the current also changes. And it is again connected with the switch. The switch is closed, the circuit is closed, the current flows through it. Otherwise, the current does not flow through it. Okay, by for varying the current, we are making all these arrangements. Clear? Now, if I change the current here, if I vary the resistance here, what happens? It is rheostat. Yeah, you can call it as a rheostat also. Okay. When this rheostat, okay, when if I vary the resistance here using a rheostat, what happens? The current flowing through this conductor changes. Now, as the current flowing through this conductor changes, what happens? The flux linking with the coil changes. Okay. As there is the change in the flux linking with the coil, a EMF is induced. We call that as self-induced EMF. Okay. If the current in the coil changes, the flux linked with the coil also changes, which results in the production of the EMF. This is called self-induced EMF. Or we know always by Faraday's law, E is equal to N d phi by dt. And induced EMF is going to have opposite direction. So we will be writing it as E is equal to minus N d phi by dt. Okay. Now, the next. Now we will be defining a factor called self-inductance. Okay, self-inductance is represented by L. Okay, and it is given by, we can write it as like this. See, we already know according to Faraday's law, E is equal to N d phi by dt. Okay. Now, by the principle of self-induced EMF, we can also write the EMF E is proportional to the rate of change of current di by dt. Why we are writing this is, when there is going to be the change in current, the EMF also gets changed, right? Ah, this is phi ma. This is the rate of change of flux. Okay, E is proportional to di by dt. So to remove this, what I will do, I will introduce a constant called as self-inductance, such that I will write E is equal to L into di by dt. Okay. Now this is also EMF and this is also EMF. So what I will do, I will equate all the right hand sides together. So N d phi by dt is equal to L into di by dt. Okay. Now considering the rate of change is going to be very negligible. So d by dt I'm going to neglect. So I will take it as N phi is equal to L into I. Okay. Or the inductance L is equal to N phi by I. Okay. So this is how you give the final expression for self-inductance L. Okay, L is equal to flux linkage by current. What is flux linkage? Flux linkage is equal to the product of number of turns into flux. Clear? N into phi by I. So here L is going to be the self-inductance. N is the number of turns. Okay. And phi is the flux. The unit is going to be Webers. I is the current measured. Okay. The unit is going to be amperes. Clear? This is how you calculate the self-inductance. L is equal to N phi by I. The same thing we had derived here. We will just go through it before moving to the next one. Okay. The property of the coil that opposes any change in the amount of current flowing through it is called self-inductance. See, we have previously defined self-induced EMF. Okay, self-induced EMF is EL. E. Okay. The self-inductance is represented by L. Okay. It depends upon the shape of the coil and number of turns. First one. Next, relative permeability of the magnetic material. Next, speed in which the magnetic field changes. Okay, so equations for the self-inductance. Let N be the number of turns in the coil. Whatever I have derived, the same thing we are going to brush it before going to the next one. Let N number of turns in the coil. Okay, assume this coil here, it is going to be N. Here the number of turns is going to be N, and the current flowing, let us take it as I. Okay. So for this, we are going to define. So E is equal to N into d phi by dt. Clear? Or the flux linkage is proportional to I, or E is proportional to di by dt. So equating this both, we will be having E is equal to E is equal to L di by dt. Okay, L is going to be the self-inductance. We are defining E is see, initially we are telling E is proportional to di by dt. That is because when the current is going to be changed, the EMF is also going to be changed. So only we call it as E is proportional to di by dt. To remove the constant, we are introducing a to remove the proportionality, we are introducing a constant L. Okay. Now this L is going to be called as the self-inductance. Okay. Or the second one, but from Faraday's law, we know E is equal to N into d phi by dt. Okay. Now equating this both, d into Li by dt is equal to d into N phi by dt, or Li is equal to N phi. Okay, or L is equal to N phi by I, where N phi is called as the flux linkage. Okay. This is one formula for self-inductance. The next one, we already know phi is equal to B into A, right? Phi is equal to B into A. Okay. What is B, ma? What is B? Put me in the chat box. What is B called as? B is the flux density. A is going to be the area. Okay. Now we know uh, from for B we have one more formula, mu naught mu r inch. Okay. What is mu naught? You are going to tell me of all the terms. What is mu naught? You've read already. Ma'am has taught you. What is mu naught, ma? Mu naught is going to be absolute permeability. What is the constant? What is the value for it? What is the value for it? Mu naught value? I am not getting any answer. What happened? 244 students not giving me one answer. 4 pi into 10 power minus 7. Very good. And right, very good. 4 pi into 10 power minus 7. Right. What is mu r? Mu r is called as the relative permeability. Right. What is H? What is H? What is H called as? What is H? Magnetic field strength. Right. H is the magnetic field strength. Very good. Now this A, I will have it as the same. 1 minute. Okay. Now we know H is given by Ni by L. Okay. So I will write it as, for this H, I will substitute Ni by L. Okay. N is the number of turns, I is the current flowing through it, and L is the length of the conductor. Okay. Now this is the value for flux, right? Now we already know L is equal to N phi by I. We have derived now previously. Okay. So in this L is equal to N phi by I am going to substitute this value. For the flux value, I am going to substitute mu naught mu r Ni by L. Okay. So this is equal to, ma'am, I'm audible, ma'am?
Ma'am, you are audible, ma'am.
Okay. Right, I'm going to substitute this value. So this is equal to N, 1 second. N into mu naught mu r n I by L into I, and you have a area here. Okay, so what happens, this current is going to get cancelled, so you will have this as n square. Okay, you have two n's here, right? So n square I call, and denominator you have L. So what is L by mu naught mu r a? L by mu naught mu r a, we have already, ma'am has taught you, this is going to be the expression for S. So L is equal to n square by S. This is the one more formula for self-inductance, n square by S. Okay, so we have read two formulas for self-inductance. L is equal to n phi by I, and L is equal to n square by S. Okay, right. Any doubts you have as of now? You can post me in the chat box. Right. The same expression one more time. See, we know H is equal to Ni by L. Okay, or B is equal to mu naught mu r H. Now here in the term, in place of H, I'm going to substitute Ni by L. So this will be mu naught mu r Ni by L. Okay, or flux is also given by magnetic flux density into area. So here in the place of B, we are going to substitute mu naught mu Ni by L into A. Okay, now this is substituted in the main formula of L. L is equal to n phi by I, and rearranging we get L is equal to n square by S. Okay, any doubts here, ma? You can post me in the chat box. So as of now, we are today we have discussed what is induced EMF, what are the major classification of the induced EMF, right? The statically induced EMF and the dynamic induced EMF, and again classification and self-induced EMF and mutually induced EMF. So in this we have read till self-induced EMF. Expressions for self-induced EMF we have done. Okay, and expressions for self-inductance. L is equal to n phi by I, or L is equal to n square by S. Okay, any doubt here, you can just let me know. Someone raised hand